G'day folks, today we're going to continue our discussion of infectious disease modelling, and our goal is to develop some mathematical models that describe the spread of an infectious disease through a population. In the previous video we talked about the basic SIR models, and they, if you will recall, deal with a population of a fixed size that we split into three portions. We have people who are susceptible to the disease, people who are currently infected with the disease, and then people who have either recovered from the disease or are removed from the population because they've died. We derived this set of nonlinear coupled differential equations to describe it, this system, and that involves two unknown constants, A and B, that are parameters of the system. They're positive. And these are functions of time. So S, I, and R are all functions of time. And the model, if you will recall, we started with the assumption that we have N people, and people who are susceptible can get the disease, and then eventually they may recover, but people who have recovered cannot be reinfected. So the arrows represent the movement between population groups. The only movement that's possible is from susceptible through infected into the recovered and removed group. And that's the basic outline of our model, and we arrived at this system of equations to describe it. So to extend our kind of introduction again to this model, remember that the A and B themselves were derived from quantities that are physically related to the spread of the disease. So we had this total population, we're calling it N, we're assuming it's constant for these models, and we introduced three parameters. The number gamma, which is the duration of infection, and tau was the probability of transmission. So if you have an interaction between an infected person and a susceptible person, that doesn't always lead to an infection. So what's the probability of an infection actually occurring there? And kappa here is the number of contacts per infected person, per unit time, which I didn't write there, but this is per unit time as well. So that's the number of interactions that infected people have with people in the general population. And so if they're interacting with susceptible people, there's some probability they'll then pass the disease on. And when we set the model up, we define these constants A and B. Just for convenience, we introduced A's and B's here, but they are related to those physical parameters of the model. A is the transmission rate, and it's the product of the number of infections times the probability, the number of contacts times the probability of transmission divided by the total population. And then this B is, of course, the recovery rate, which takes people, so we basically, A is the parameter that's modeling this motion, and then B is the parameter that is controlling the recovery. So with this understanding of the disease, let's first talk about the mathematical properties of this system of equations. So we're talking about this system of equations, and an important mathematical question about differential equations is whether they're well posed, which has technical meanings. Does a solution exist? Is that solution continuously dependent on the initial conditions and that kind of thing? We're not going to worry about those. The theory of differential equations tells us that this is in fact a well-posed system in that sense. For this course, we're going to worry about whether these equations are well posed in a physical sense, in that it keeps the number of susceptible, infected, and recovered people greater than or equal to 0, because it's a count of people, so you can't have negative people. And also we started with a population of n, so none of these variables independently can be bigger than n. Right? So I want to know, do my differential equations make sure that this condition is true? Now we already saw in the last lecture that the rate of change of the sum of these things is 0, and that tells us that the sum of the variables, s plus I plus r, is equal to n for all t. In other words, we started with n people, and for all time we have the n people split between these three groups. Well, that could go wrong, because although I know they add to n, what happens if one of them's negative? Because if one of them's negative, then another one of them may be bigger than n. You can't have a negative number of people. You can't have any of them bigger than n. These are physical constraints we have on the system. But this equation by itself, the fact that the sum of the variables adds up to n, isn't quite enough. So what I want to actually know, what I want to actually convince ourselves of, is that each of these variables remains greater than or equal to 0. So as I'm evolving with this set of equations, I get a set of variables that are greater than or equal to 0 for all time. So we're going to start by thinking about a set of initial conditions for these differential equations. In other words, at time 0, then the number of susceptible people is S sub 0, infected is I sub 0, recovered or removed is R sub 0. And we're going to imagine what happens as time goes forward. So we're interested in seeing what happens for all time greater than or equal to 0. And we're going to think about phase space. Now we saw in previous sections, we talked about phase diagrams where we had x's and y's and they were functions of t, and we saw spirals and things. So time was flowing as we moved around that that picture. And this is what we called a phase plane. Well, it's a plane because it's 2D. Now we're moving over here to phase space because we have 3 variables. We have the number of susceptibles, the number of infected, and the number of recovered removeds. So we're going to move into this phase space instead of the phase plane, and we're going to think about what happens. So at some moment, I'm thinking about, I've got this point, at some moment, I'm sitting at some point up here. Right? This is the number of susceptibles to begin with. This is the number of infecteds to begin with. If I finished a kind of cube here, if you've taken Calc 3, this picture is not very surprising to you. If you haven't, don't worry about it. All I'm doing is drawing a point in space. And so that's my starting point, right? That is my initial condition, which I describe with the 3 numbers. And those 3 numbers just give the number of infected, the number of susceptible, and the number of removed at time 0. And then what I want to know is what happens in time. In other words, this set of differential equations is going to change S and I and R as time goes by. And what that corresponds to is this point wandering around in phase space, right? Because changing S and I and R is just going to move us on the various axes. So the trajectories in phase space, these are going to be now trajectories in 3 dimensions. But those trajectories describe the whole curve. What I want is to make sure that S and I and R are never bigger than n. And because I know they add up to n, they always add up to n, that follows directly from the differential equations. So the fact that I know they add up to n, if I just can show that they're never negative, then I know that they all must be less than or equal to n, because the 3 of them together are positive, and yet 3 of them together never add up to anything bigger than n. So the worst case is, 2 of them are 0 and 1 of them's n. Or you can have a split between them. So the thing I want to show here is that I never get negative S or I or R. So the differential equation is going to govern how I move around with time. Moving around this curve is, in other words, just time changing. So as time changes, I move around in space. Do I ever leave this first quadrant? Because I want to show that they're always not negative. So let's imagine one of them was 0. Let's suppose that this trajectory, kept winding around, and eventually S equals 0 is going to be this back plane here. So let's suppose eventually S was 0 and I went back there and went bang on the back wall. So I'm on this back wall where S is 0, right? S equals 0 is literally the entire plane up here. So S equals 0 is all the points here because I'm on 0 on the S axis, I and R could be anything. So let's say there's some moment when I hit that plane and S is equal to 0. Let's look at the differential equations and see what they tell us. Well, if I look at this first equation and I know S is 0, then I know this is going to be 0 because whatever I is, S is 0. So ds dt is going to be 0. So if I'm on this plane where S is 0, then ds dt is equal to 0. And so S is equal to 0 for all time. Think about what that means. If for some reason I happen to be moving around in space here and I end up on the plane at some moment, right? At some moment I end up sitting on this plane where S is 0, then I and R might continue changing, but I have to remain on the plane because S stays 0 for all time. So if I hit that plane, if S is ever 0, in other words, there are no susceptible people left, then it must be 0 for all time. You can't generate new susceptible people. And so that's it. So S can never be negative because worst case it gets to be 0 and then it stays 0 forever. What happens if the number of infected people is 0? And in this case, the number of infected people, we're talking about the plane down here. This is the plane where the number of infected people is 0, but the number of removed and the number of susceptible people can be any value you like. Now, if you go to the differential equations and you look at the rate of change of I with respect to t, when I is equal to 0, well, both of those terms involve an I, and so that means the rate of change of I is 0. So if I is ever 0, then I is 0 for all time thereafter. And so once again, if I were to bang into that sidewall, I can't cross it. I can never become negative, because once I end up at a point where I is 0, then I have I equals 0 for all time. So what about the last one? We now know that the number of susceptibles can't be 0, the number of infecteds can't be 0. What about the number of removed? Well, in that case, if the number of removed is equal to 0, I'm talking about being on the floor down here. This plane down here is where the number of removed are equal to 0. So I'm talking about some point literally there. Well, if the number of removes are equal to 0, you can see that the rate of change of the number of removes then is going to be, well, it's going to be b times I. B is a positive number, right? Because we define that in the model. I is a positive number because we just said it can't be negative. You know, the argument for these first two is all about if I start in this first octant, where I and S and R are all positive to begin with, then I can't leave that octant. So I has to be at worst 0 or positive. So B and I are both positive, which means this is positive. Worst case, it's 0. And that means R is increasing or stays where it is. If it's increasing, then we're wandering upwards, right? Because R is the height off the ground. So R increases. So if R is ever 0, then it either remains fixed in the special case when I is also 0, because then this rate of change is 0, or it increases because I and B are both positive, so R is an increasing function. So if it's ever 0, it's probably just going to get bigger. And so it can never be negative. And so I have three numbers that are all positive. I now know that for certain. They're all positive, and the sum of the three of them add up to n. So I know that this condition on the S and the I and the R is held, but is maintained by the differential equations. Those differential equations keep the variables in that physical sense. They keep them so that they're greater than or equal to 0 and less than or equal to n. And I could actually go a step further if you wanted to think about the points on these axes where the population is exactly n. So right here the number of recovered is n, with 0 susceptible and 0 infected, whereas down here I've got susceptible people, n susceptible people. I could build a plane that joins those points. And that plane is literally, again, this is if you know Calc 3, then this plane, S plus I plus R equals n, looks like that. And so looking at it just a bit more clearly, that condition that the sum of S and I and R is equal to n means that we get this plane. So essentially we've got a roof. We know that S and R and I are all greater than or equal to 0, and the sum of them is equal to n. So the trajectories wander around inside that triangle. Right? The trajectories have to be below that roof, so I'm going to have some point here. And the trajectories are wandering around inside this triangle, so below that purple triangle, above the floor, inside just that tetrahedron. Right? So the phase space for this system is literally limited to being inside that kind of tetrahedron that I've drawn there badly. So that's the phase space. All right, that's just kind of a fun visualization. Let's use this to look a bit more deeply at what these quantities mean. So what we want to do next is think about what the solutions of this actually look like. And the way we've been doing that in previous sections is by doing a graphical analysis. So we can do a graphical analysis on this system in 3 space, which we were just thinking about. But if you look at this last equation, it's kind of redundant because we know that R plus I plus S is equal to n. And so I could replace, and n is a constant, and that's terrible handwriting, but if I know what S and I are, then I can calculate R. It's just what's left out of the population. It's everyone in the population who's not susceptible or infected. It's the ones who recover. They're just the people left over from that group. So in a sense, if I know what S and I are, then I can calculate R without solving a differential equation. And R does not explicitly appear in these first 2 equations. So I can drop the equation. Because once I solve the 2 equations by themselves, and n is fixed, I can always just solve for R. I can calculate what R is at any time. So these 2 equations are enough, and this is exactly the kind of system we've been doing graphical analysis on. So let's rewrite them by just factoring. I'm factoring here the A and the I out from the first term, just leaving the S, and then the second term, that's going to leave a B over A. Multiply back in, and you'll see that that's the right system. But from here we can see the equilibrium values, right? we can see the equilibrium values from the first order from the system, and remember equilibrium values are where the derivatives are zero, which in this case, from the first equation, we're going to have the condition that A times S times I is equal to zero. Right, just looking at our equilibrium values, and that leads to two conditions, either S is equal to zero or I is equal to zero. And then if we look at the second equation, if S is equal to zero, the second equation tells us that A, and by equations I mean, I'm setting these to zero. And so from the second one, if S is equal to zero, then I've got A times I, 0 minus B over A is equal to 0. A and B are non-zero constants, so the only possibility there is that I is 0. And from the second one, I is already 0, and then equation 2 tells us that 0, well, A times 0 times whatever's in the brackets, well, that's equal to 0. So that's true for all S, right? So I equals 0 is a special case that makes both equations true. So the only equilibrium points are along the line I equals 0. So sketching this back in our phase plane, the line I equals 0 is literally the x-axis, in this case the s-axis. So I equals 0 and s equals 0 is that point there. But in fact the entire line is a line of equilibrium points for any value of s. So if I is equal to 0, then the rate of change of s is 0, the rate of change of I is 0. So if I'm on a point here, I stay there forever. Looking at these equations, you can see there's also something interesting happening when s is equal to 0. We've got along the line where s is 0, which is the y-axis there, the rate of change of s will be 0. And then when s is equal to this value, and let me write it down here, when s is equal to b over a, we see that the rate of change of I is 0. So there's a special value of s. Let me draw in that special value of s. There it is. This is the line where s is equal to b over a. And when that happens, the rate of change of I is 0. And then over here, along the line where s is equal to 0, we also have the rate of change of s being 0. So let me sketch this on the next page a bit more neatly. So here's our phase space. We know we have a line of equilibrium points along the s-axis down here. We know the maximum population that we can have in any category is n, because that's the total population overall. Let's think about initial conditions for a second. At the beginning of an epidemic, you don't expect there to be anyone recovered from the disease. So I'm going to say that at the beginning, the number of recovered people is 0. Right, that seems reasonable. And then you've got some susceptible people, probably most of the population, and then an infected person or 2 or 3 or 10, who knows. But at the beginning of an epidemic, I imagine I naught would be small and most people would be susceptible. But regardless, the sum of those two has to be n. And this is a straight line on the axis, right? If I drew that line on the axes here, then I've got a line that passes through those two values of n. So this is the curve s plus I equals n. And now to begin with, I'm going to start on that line because my initial condition, those two numbers have to sum to n. The number of susceptible initially plus the number of initially infected people must sum to n. So all my initial conditions will start on that line. And all our trajectories will be below the line, right? Because we need to keep the sum of those two things less than n. And if I get above that line, then the sum is bigger than n. If I'm out here, then I've got more than n susceptible. If I'm over here, I've got more than n infected people. So my trajectories are going to live on that line. And just for completeness, to make this nicer, I'm going to move that a little so I can get a better view. All right, so this is our special value of s. This is the value b over a. Let's see what happens. Doing graphical analysis, I'm just going to go through these different regions. I know s is always positive, and I is always positive, and a is always positive, so s is always negative. S is always decreasing. We're always moving to the left. Right? For every value of s and I that I care about, they're positive. A is positive, so s is decreasing. The number of susceptible people decreases with time, which is the only possibility, right? Because the susceptible people become sick. And so the only possibility is that the number of susceptible people reduces in time, decreases. We can read that straight off the differential equation. S of t is a decreasing function for all time. Now, so what really matters is what I is doing. And looking at this equation, A and I are always positive, so the deciding factor is what's happening with S. So if S is bigger than B over A, then the rate of change of I, so over here, S is bigger than B over A, which means the rate of change of I is positive. Whereas over here, where S is less than B over A, because remember, this is the line B over A, so in this region, dy dt is negative because S is smaller than B over A, so we're subtracting B over A. So in other words, we're always moving to the left, but in this region we're moving down, and in this region we're moving up, right? I is increasing, so we're moving up here. I is decreasing, so we're moving down there. When S is exactly equal to B over A, then we're moving exactly left and right because I is not changing at all. And so along this line, we're moving exactly, in this case, to the left because S is always decreasing, right? ds dt is always negative, so we're always moving to the left. Let's draw some trajectories. Every single trajectory starts on this line because that's where the sum of I and S is equal to the total population. We have no people who are, we have no people who are recovered at this stage. So our little trajectories are showing that in this region, we're moving up and to the left. So we're going up and to the left until we get to this line where we stop moving up and now we start moving down. So it's got to look something like this. If I think about a trajectory that starts here, what about if I start here where everybody's infected and there are no susceptibles? Well, then the trajectory is going to move straight down, right? Because when I is equal to 0, S isn't changing, so we're moving up and down this line, but I is equal to 0, S is equal to 0, this line is S equals 0. When S is equal to 0, S doesn't change, and so we're stuck on this line. But when S is equal to 0, this is negative, and so the trajectories on this line, the line where S is equal to 0, are straight down towards that fixed point there. So if I hit that line, if I hit the y-axis, we're heading straight down. So this must curve around because it can't cross this, because if I get there, I'm going straight down. So at any point where I start, if I'm starting down here, then I'm going up for a while until I get to the line where S equals A, in which case I'm going straight across, and then we're going down. If I start on a region up here though, I'm already heading down and to the left. So these trajectories must go like that. If I start with trajectories there, I'm going straight down, right? Trajectory there, I'm going straight down. If I'm at this exact point, then I'm temporarily flat and then going down. So my trajectories must be looking something like this. If I start really close to the line over there, I'm going to just increase till I hit that curve, and then we're going to start coming down. So notice what all of these trajectories are doing. There's two important things to notice here, at least two. S decreases, we know that, right? S is a decreasing function. We're always moving to the left. But more importantly, I eventually decreases. It might go up for a while here. We're increasing, we're heading up the y-axis, I is increasing. If I'm starting at any point along this line, I'm going to increase for a while until I hit that curve, and then I'm going to bend downwards. And so I is eventually going to decrease. All of these things are leading us down here somewhere. The question is, what does that mean? Can you see what's happening? This is the number of infected people. If I start in this region, then the number of infected people is growing with time because time corresponds to moving along these blue lines, these trajectories. So if I start at this point, then the number of infected people is growing while the number of susceptible people is decreasing. So the number of infected people is growing until I get to this line, at which point the number of infected people stop growing because on that line I know that the rate of change of the number of infected people is equal to 0. Oh wow! That means the number of infected people must be a maximum there. You can see it on the picture, right? This is the point where the number of infected people is maximum on that trajectory. If I start down here, the number of infected people grow until I get to this point and then start shrinking. You can see that this model represents an epidemic. Because by definition, an epidemic is something where the number of infected people grow, but then eventually the disease dies out. Right? So this is an epidemic because, well, literally, all of the susceptible people look like they're going to 0. Right? These trajectories have a maximum number of infected people, and then the number of infected people start to drop off. When does that happen? Well, it happens when the rate of change of I with t is equal to 0. When you hit the maximum infected people, well, you hit the maximum number of infected people when S is equal to B over A. And so this is our condition. Look at the trajectories on the left of that line. Over here, every single one of those trajectories just decreases from the start. If I start my epidemic in a point here, with this number of susceptible people and this number of infected people, if my epidemic starts here, then it doesn't spread, it just dies out. the maximum number of infected people I had was on the first day, and it just goes down from there. Whereas if I start my epidemic over here, then the epidemic gets worse and worse and worse until I hit the maximum number of infected people, but then the epidemic dies out, right? And when does you hit the maximum number? You hit the maximum number at this ratio. And more importantly, if I start with the number of susceptible people past smaller than that number, then the epidemic is never really takes off, because the population just starts decreasing. The population of sick people, I, starts decreasing immediately. Whereas if I start on this side, where S is bigger than B over A, then the number of infected people is going to get worse, potentially for quite a while, before it starts dying off. So this gives us a real insight. We can see there's a threshold here. There's a difference in the behavior of the disease based on whether you're to the left or the right of this line. Because if you're to the left of this line, the disease is going to have the most infected people on day one, and then it's just going to slowly peter out. Whereas if you start on the right of this line, and realistically you're going to start way down here with maybe one infected person and almost everybody not infected, then the disease is going to grow for a long time, get worse and worse and worse. This is what we're seeing with COVID-19, right? The number of people is increasing over time to the point that the medical system can't cope with the number of sick people. So this is the case you don't want. And so let's think a bit more about that condition, because the condition is literally whether or not we're to the left or to the right of that line. So summarizing what we just saw, we have two general kinds of trajectories. We have the ones that start over here, where this is our S naught, right? Our S naught and I naught. S naught is the number of susceptible people at the beginning of the epidemic. Here's a different S naught. It's the number of susceptible people at the beginning of the epidemic, but you see it's much smaller. If I start with my number of susceptible people here, then you can see that an epidemic is going to occur, an outbreak is going to occur. We're going to increase the number of infected people for a long time, presumably before we hit the maximum and the number of infected people start dying out, or not dying out, but the number of infected people reduce. Whereas if my epidemic starts up here, then the number of infected people at any given time will decrease with time. Whereas over here, the number of infected people with time will increase for a while. And so what's that condition? We need S naught for an epidemic to occur. In other words, for the disease to be spreading and really infecting lots of people, we need S naught to actually be bigger than B over A, because that's our condition up there, right? In other words, S naught is bigger than B over A is a threshold. If S naught, so this is the initial number of susceptible people. We need the initial number of susceptible people to be bigger than B over A, and B over A, remember, is related to those fundamental constants of the system. So N is the number of people, kappa is the number of contacts, tau is the probability of spread, and gamma is the time length of the disease, how long you stay sick. So as long as S naught is bigger than B over A for a disease, we're going to get an epidemic, right? The disease is going to get worse. The number of infected people is going to increase with time. And there's something amazing about this. This doesn't depend on the number of infected people you start with, right? And this might be counterintuitive. It probably is counterintuitive. It doesn't matter if I started with one infected person or 100 infected people. My model tells me that what matters in terms of what's going to cause an epidemic, what matters is how many susceptible people I have to begin with, how many people are available to get sick, if you like. And if the number of people who are available to get sick is bigger than B over A, then you're going to have a bad disease where the number of infected people increases with time. But if you don't have enough people to get sick, if S naught is not bigger than B over A, then the disease is just going to slowly die out because the number of infected people is just going to rapidly decrease. So what we've seen today is that our graphical analysis skills lets us analyze these basic SIR models, and we see that there's a threshold. There are two types of trajectory depending on the value of S sub 0, right, related to the parameters of the model. We see that if S sub 0 is small enough, the disease is going to peter out, but if S sub 0 is large enough, in other words, there are lots of susceptible people to begin with, then the disease can take off and cause many, many infections. We're going to talk more about this threshold next time. We're going to relate it to these basic parameters and talk about what it means in a physical sense for the epidemiology and for the properties of the disease. In the meantime, thanks for tuning in. I hope you have a wonderful day.